I think it's a good idea to take advantage of this session to make a review. So what we're going to do is we are going to review all the most important concepts we have covered during the first weeks of this course. So this course is, or this module is about introduction to structures. So it's very basic in terms of knowledge and concepts, but it's a good idea to start from the beginning. So the first thing that you need to remember and you need to take into consideration when you resolve the structures into dimensions is that we have to decide what is the convention we are going to use for the direction of forces and for the direction of rotations, or and I'm mixing here because forces will produce displacement. So what we do in terms of convention in this module is to consider that all the forces that goes to the right are positive. So the forces that go to the left will be negative, of course. All the forces that go up are positive, and the forces that go down will be negative. And these forces will produce horizontal displacements that will be positive when they go to the right. Displacement will be negative in the horizontal direction when they go to the left. And in the same way, displacement that goes up, because forces that go up will be positive. Displacement that go down in the vertical direction will be negative. Moments and rotations, clockwise rotation or clockwise moment will be positive. Evidently, yes. So evidently, rotations and moments that go anti-clockwise will be negative. So we need to take this in mind because it's important to assign the proper or the exact sign to every term of our equation, because if not, we are going to make mistakes basically. So I have chosen to work today with two examples you have in your notes. So the example 3, that is this cantilever beam you see in this on the screen. And before starting the example, remember that even when we work in 2 dimensions, there is a third axis in the 3-dimensional space, an axis that is perpendicular to the screen, and I put in here in red. And this is the axis around the moments acts. For example, this negative moment of 40 kilonewton per meter is a negative moment because it's anti-clockwise and produces rotations around the axis perpendicular to the screen that is in red in here. For simplification, we are going to call for now the horizontal axis or H, and the vertical axis V, or vertical axis. But you can choose to work with X, Y, Z, Y, or any combination the 3-dimensional coordinate system has for you to choose. So the first example is a cantilever beam. So if we want to be pure and, let's say, mathematically consistent, we should say that 60 kilonewton, this punctual load, is negative because it's coming down. This moment, 40 kilonewton per meter, is negative because it's anti-clockwise. This 12 kilonewtons per meter should be negative because it's going down. And there is a mistake in here because this is not negative, this is positive. 40 kilonewton is positive because it's going up. 70 kilonewton per meter is positive as well because it's clockwise. So what I'm going to do, I will correct this one because this is incorrect. So now everything is correct. So with the sign and the directions shown in with the arrows. So the other thing that is extremely important for you to remember, especially when you write down your exams is to use the units, the proper units. So the first scheme where the problem is shown, at least need to have all the units declared for me to be sure that you are working with the units you are supposed to be working. In any case, you need to be consistent. When you use meters for every single distance, and you use the unit for the force multiplied by meters. For the forces, we're using kilonewtons in these examples and across the whole course. So kilonewtons per meter is the unit for moments, kilonewtons is the unit for forces, and meters is the unit for distances. The first step in every exercise is to produce the free body diagram. So the free body diagram is a diagram that replaces the first scheme you have in here. This is the scheme where we can identify that there is a fixed support to the left extreme of the beam. Then this means that we are going to have three reactions at this point, because we know the way this fixed support works. So restrict the 3 degrees of freedom of this beam. So we produce 3 reactions: an horizontal reaction, a vertical reaction, and a reaction as a moment at the exactly point A where the fixed support is applied. Again, you see that here that I have deleted again the signs of the forces, because in engineering, in order to avoid confusions, we sometimes prefer not to put the sign of the force, but show the force with its direction. For example, in here it's clear that this force is coming down, so it's negative. And we are going to take into consideration the signs only when we write equations. So in this cantilever beam, we will have to calculate these reactions to the left extreme of the beam. But initially, when we decide the direction of this reaction, we don't know if these reactions are shown in the right direction or not. The equation will tell us if the direction are right or are wrong. And we're going to see this in this example. This example as well is good because it has all the forces, typology of forces you will have in this exercise. This is, for example, you have punctual load, you have moments applied to certain point of the structure, for example, these 2 points in here. You have UDL, uniformly distributed loads. And the other thing that you need to remember when you are using UDLs, as the UDL can be replaced by a punctual load that will be equal to the value of the load per unit of length multiplied by the distance where the UDL is applied. In this case, is 2 meters. So 12 times 2 is equal to 24. So you can replace the effect of this UDL by this punctual load of 24 kilonewtons applied in the middle of the UDL itself. We do that because it's simpler to write equations when you refer to punctual loads instead of the UDLs directly. When you have practice, you can do it directly without simplifying in this way. But for the moment, it's a good practice for you because you are starting learning structures that you replace this UDL for the calculation, for this punctual load for the calculation of reactions. So once we have decided the direction of these reactions to the left extreme of this cantilever beam, you can start writing the equations of equilibrium. So we have said in the previous week that equilibrium is the most important principle we are going to use in our calculations in this subject. So the equilibrium is written in a form of a mathematical set of 3 equations: summation of forces in the horizontal direction plus the summation of forces in the vertical direction plus summation of moments around a point in the structure. This doesn't mean you cannot use other equations because there are more equations to resolve this structure. But these equations in this case, because this is a cantilever beam, are the most reasonable equation to use. And you see that because when you apply them, you extract the value of every direction from every equation. So these equations are very useful, and it's a straight, the calculation is a straight away because of this. So when we do the summation of forces in the horizontal direction in this cantilever beam, we realize that because the only force in the horizontal direction is the reaction H, the equation for the equilibrium in the horizontal direction will be H equal to 0 only, because there is no any other component acting in the horizontal direction. All the other forces are acting in the vertical direction, or they are moments. So the only force in the horizontal direction is H. So in order to fulfill the summation of forces in the horizontal direction is equal to 0, which is a mandatory equation that you need to fulfill because it's the principle of equilibrium, the only possibility is that the reaction is equal to 0. So the first reaction for this beam in the horizontal direction is equal to 0. When we do the summation of forces in the vertical direction, we need to take into consideration the sign of the forces. This is the reason why in this equation V, the reaction we are calculating is positive, because we have chosen to give the force this positive direction. 60 is negative because it's coming down. 24, the equivalent punctual load to work with the UDL is negative force. 40 is positive because it's going up, and all of this is equal to 0. You can see that in this equation, any moment have appeared because this is summation of forces. So when you do summation of forces, you ignore any moment applied at any point of the structure because they are moments, they are not forces. In the same way, you didn't include in your equation the moments as a reaction in here because it's a moment and we are doing summation of forces in the vertical direction. Once we have the equation of the summation of forces in the vertical direction, we just work out or rearrange this equation, and we are going to have that the V is equal to 60 plus 24 minus 40, which is equal to 44 kilonewtons. Again, very important for you to declare the units of your results, because if not, this response will be incomplete. Well, we have used the summation of forces in the horizontal direction and in the vertical direction. So now it's time to apply the summation of moments to calculate the moments as a reaction in red you have on the screen. So in cantilever beams, we choose to do summation of moments at the point where the fixed support is applied. So we are going to do summation of moments around the point A, and these summation of moments need to be equal to 0. This is again mandatory because this is the principle we are using. So the first moment we see when we are located at A, at the point A, is the moment as a reaction M, and we have decided that this moment is negative because we need to decide in one direction. So it's minus M for this reason. The first moment we see is produced around the point A, is we go from left to right on the structure, is 60 kilonewtons multiplied by 2 meters, the perpendicular distance to 60 kilonewtons. So, and this product, kilonewtons per meter, is a moment, and it's a positive moment because if you check the rotation, this force produced around the point A is a clockwise rotation. So it's a clockwise moment as well. The next moment we see is this moment applied at this point in particular is 40, but it's negative because it's anti-clockwise. And this is the reason why this 40 is negative in your equation. The next moments around the point A will be the moment produced by the UDL, but this moment is equivalent to the moment produced by the equivalent load. And this is the reason why we use 24 multiplied by 6, the distance to the point A, positive because it's clockwise, and this is the term that represents the moment of the UDL. The moment produced by 40, this force that is going up, will be 40 multiplied by the distance from 40 to A, which is 8. And it's negative because the rotation that produced around the point A is anti-clockwise. And finally, we have this 70 kilonewtons per meter applied to the right extreme of the cantilever beam. It's a positive moment because it's clockwise, producing rotations in the clockwise direction. So plus 70, all of this equal to 0. From this equation, if we move this minus m to the other member will be m equal to all of these you have in here in this equation. Working out the value, you find that the moment is equal to minus 26. So when resolving an equation of equilibrium, you receive a negative result, automatically you pay attention and you say, okay, because this result is negative, this means that the direction of the moment I have chosen is not the right one, it's exactly the opposite. So you have to change the direction of the moment, correct in your free body diagram, the direction of the moment in this case. And if you rewrite the equation of moment, you will notice that now m is positive. All the other signs are correct because you didn't change the direction of any force of moment. And now when you work out the value of m, the sign of your moment is positive. This means that 26 kilonewton per meter, the moment as a reaction at the point A, have this clockwise direction and not the anti-clockwise direction we have chosen from the beginning. So this proves that it doesn't matter the direction you choose when you initially set the free body diagram. What is important that you work with the equations and you connect the equations with the free body diagram to be sure that the directions are right, because it's not only about the values, it's as well about the directions. And this is important because, of course, after the calculation of the reactions, we need to produce the shear force diagram, the axial force diagrams, and the bending moment diagrams. And if you have the wrong directions for your moments and reactions, the diagrams will be wrong as well, because the diagrams have signs as well. So the first task is done because we have 3 tasks basically on this beam, because these are the 3 topics we have covered. So we have resolved the equations now. In the next, we are going to resolve the shear force diagram, and after that, the bending moment diagram. Good. So now we have the reaction. So not only the direction, we have the values. We have deleted the horizontal reaction because it's equal to 0. So I have only this vertical reaction equal to 44 kilonewtons and this positive moment equal to 26 kilonewton per meter. So in order to sketch the shear force diagram, because we have learned a few things already about the shear force diagram, what we need to anticipate are the changes, the sudden changes we are going to see in this diagram. So in the first place, we need to sketch this horizontal line that represents the neutral axis. You will understand why it's called neutral axis in the second semester. But it's a horizontal line for now that represents the beam and is the reference for our diagrams, because in the diagram we're going to sketch the values of the shear force at every cross section of this cantilever beam. And we expect to have sudden changes in this diagram at the beginning where the reaction is applied, under every punctual load, because the punctual load affects severely the value of the shape of the diagram. You see that the moment won't produce any influence on the shear force diagrams. We can ignore this moment because the shear force diagram is not affected by the moments at all. An important point where we're going to see changes is the initial point of the UDL and the final point of the UDL, where the UDL is applied. Again, this punctual load, and of course the end of the beam is an important point as the beginning of the beam, because they just are point where you close the diagram, we say. So once we have these references, remember that it's a very good practice and it's extremely important actually to read this properly, that the diagram is aligned with the structure. So we need to use a scale, the same scale for lengths in the scheme and in the shear force diagram and the bending moment diagram after. So we will usually start from left to right. This is the way I like to do it. You can do it from right to left if you want. But for me, it's simpler if I do this, these diagrams from left to right. So one way of producing the shear force diagram is starting from the reaction to the left. For example, in this case, I will start adding the reaction at the first point of this diagram. So it's 44 kilonewtons. And after that, I know that in between forces, the shear force diagram is constant. And the reason why it's constant is because if I locate myself in every cross section in the middle, in between these two forces, 44 kilonewton the reaction and 60 kilonewton the action, and I do the summation of forces to the left, for example, I am in the middle here, in between these loads, if I check the summation of shear forces to the left, which are the vertical forces only, because the cross section is vertical, the only force is 44 kilonewtons. So evidently, the shear force will be constant from here to here. And this is what I'm adding in this diagram at the moment. So I know the first force is the reaction 44, and after that in between forces is constant. Immediately after the force 60 kilonewton, let's say I am in a cross section here, you see that the shear force is equal to 44 positive shear force minus 60. 44 minus 60 is minus 16. So the value from the neutral axis to the end of this arrow is minus 16. And in between forces again, between 60 and the initial point of the UDL, the shear force diagram will be constant. And this is the reason why I'm adding this horizontal line in here. You see that the moment, we just ignore the moment because the moment doesn't produce any effect on the shear force diagram. So then I have the shear force diagram from the beginning until the beginning of this UDL now. The next point where I have to calculate the shear force is the point at the end of the UDL. So in this case, the shear force will be, if I am here at the end of the UDL, the shear forces to the left will be 44 kilonewtons minus 60 minus 24 kilonewton, which represents the effect of this UDL. And this is the reason why you will see that at this point is minus 16, and this point will be minus 40, and the variation of the shear force diagram is linear. So as a rule, you can say in between loads, the diagram is constant. When we have a UDL, the variation is linear. And this is the reason why we connect minus this 16 with minus 40. Once I'm there, in between forces again is constant. And once we reach 40 kilonewtons, we have to add 40 kilonewtons. But the truth is that from this point to the neutral axis, we have 40 kilonewtons. So in this case, we close the diagram before ending the beam. And if you check every cross section from 40 kilonewtons to the right extreme of the beam, you see that in any case, the summation of shear forces is equal to 0. You can do it to the left or you can do it to the right. To the right is simpler because in every cross section in between 40 and 70, to the right there is nothing, so it's 0. And to the left, if you are here, for example, in the middle, in between 40 and 70, the summation of 44 kilonewtons minus 60 minus 24 plus 40 is equal to 0. And finally, you can add the sign of the shear force diagram.
Sorry, could I ask a question there?
In the screen. Yes, of course you can make a question. Tell me.
Yeah, in terms of you didn't use the 24, the force coming down from the UDL.
Yeah.
You didn't use that because you only did 44 minus 60, then you did the inclined, then you just went to 40 to close off. So that 24, should we ignore that? I mean, you didn't use it.
Yes, the value 40 here minus 40 will be equal to, if you are here at the end of the UDL, is 44 minus 60 minus 24. Because at the end of the UDL, if you are here, for example, where I'm showing you in the screen, the summation of shear forces to the left will include the whole UDL. As an exercise for you to understand how this works, you can try to calculate this value in the middle, for example, of the shear force. So if you are here, this is your cross-section. Sorry for that. So if you are in the middle of the UDL and you are doing the summation of shear forces to the left, what you will have 44 minus 60 minus half of the UDL, which is 12 multiplied by 1, or 12 kilonewtons, as you prefer. And when you do the summation of shear forces to the right, if you are in the middle of the UDL, you will have 12 times 1, positive initially, minus 40. So this will be this 28 in the middle of the UDL. The other thing you can check in here easily is you are at the end of the UDL. The only force you have to the right, the only shear force you have to the right is 40, and it's negative. And this is the reason why you have this minus 40 in here. So what I suggest to understand the construction of this shear force diagram in every single detail is to try to do the calculation of the shear forces in cross sections in the middle, in between forces, for example, to check that effectively what I'm saying is right. For example, in here, in the middle, in between A and 60, Y is 44, because to the left you have 44 only. If you do the calculation to the right, so if you are in the middle here and you take into consideration all the forces to the right, you will have to get again 44, because it's because the equilibrium, you cannot have in a cross section to the left a value and to the right another value. So it's not just constructing the shear force diagram, it's to be sure that you understand the definition of the shear force. That, remember, is a simple definition. The shear force at every cross section of a beam is the summation of shear force to the left of the cross section, or the summation to the shear forces to the right of the cross section. So once we add the signs in here, so we consider that the diagram from the neutral axis and on top is positive, and from the neutral axis to the bottom will be a negative shear force diagram. This is arbitrary, you can change it if you want, but it's important to distinguish that part of this beam is subjected to this positive shear force, part of the beam is subjected to negative shear force. Once, any questions? Okay. So once you have calculated the shear force diagram, you need to calculate, or you need to sketch the bending moment diagram. So for the bending moment diagram, the points of interest for your calculations will be the initial point of the beam, the points under the loads, the points where you have moments, because this is bending moment diagram, so the bending moments will affect the diagram, the initial point of the UDL, the final point of the UDL. You can as well add the middle point of the UDL, because now you are learning how to work with these diagrams for the first time. This other punctual in here, and the end that coincide with the moment applied at the end of the cantilever beam in this case. So the first moment we can sketch in here is this moment of 26, which is the reaction as a moment at the point A. And this moment represents the moment immediately after, in the cross section, immediately after the point where you have the moment applied. So this moment is applied exactly at the point A. So exactly at the point A, the moment is equal to 0, because actually we have used the summation of moment equal to 0 at A to calculate the moment. So evidently we cannot say that at the point A, the value of the moment is 26. This 26 is from the first cross section after the point A. So this is a detail you need to understand. So immediately after the point A, you have 26 kilonewton per meter of moment produced by the reaction, 26 kilonewton you have in here. And this moment is positive because it's close Y, and this is the reason why we are sketching the moment from the neutral axis and down, because this is the convention we are going to use in this module. So all the positive moment will be under the neutral axis, all the negative moment will be on top of the neutral axis. So once I have this value, the next point I will use to calculate moment will be the point exactly under 60 kilonewtons. So when I am 2 meters from A, at this cross section I have 26 kilonewton per meter, the moment as a reaction, but plus the moment produced by the reaction 44 kilonewtons, which is 44 kilonewtons times 2. So 26 kilonewtons plus 44 times 2 give me 114 kilonewton per meter is the moment at the cross section where we have applied 60 kilonewtons. In between forces, for the bending moment diagram, the variation is not constant because this is not a shear force diagram. The variation is linear. You can take this as a rule, but you can prove that this is right calculating at any cross section in between A and 60 kilonewton, the value of the moment, and you will see that this is a linear equation. The next point of interest, or the next 2 points of interest in terms of bending moments, is the cross section immediately before the moment applied at this point and the cross section immediately after this moment, because this moment will affect certainly the diagram. So the first point we're going to discuss is the point immediately before the moment. So at this cross section, the moment will be 26 kilonewtons, the reaction, plus 44 kilonewtons times 4, and minus 60 kilonewtons times 2, the moment produced by 60 kilonewtons. If we do that, we are going to find this value 82. And between forces, again, the variation of this moment will be linear. But before doing the variation of the moment in the interval from the 460 and the moment, we are going to calculate the moment immediately after the moment. So now we are in this cross section immediately after the moment, 40 kilonewton per meter. So the moment in the air will be 44 times 4 plus 26 minus 60 times 2 minus 40, the moment that now is included in the cross section I am analyzing. And for this reason, the moment immediately after the moment is 42. And now I can add this line of a linear variation of the moment and see what happened when you have a moment applied on a beam in terms of the diagram. Before the moment you have a value, and after the moment you have another. This is because this moment is applied exactly at a particular cross section and produce this sudden change in the diagram. The next point of interest is the initial point of the UDL, where if I do the calculations, I will have, again, I am here now at the beginning of the UDL. At that point, I have 26 kilonewtons per meter plus 44 times 5 minus 60 kilonewton times 3 meters and minus 40. And all of these give you 26 kilonewtons. Now, because I know the variation in between forces will be linear, I add the line and I have the bending moment diagram until here. The next point of interest will be the end of the UDL. If I am here now at the end of the UDL, I can do these two dots, this 30 I have calculated in here. For example, I am at the end of the UDL. The moment will be 26 times 44 times 7 minus 60 times 5 minus 40 and minus 24 times 1, because I'm using the whole UDL at this point to calculate moments. In this case, you can see that doing to the right is simpler because to the right you will have, if you are here at the end of the UDL, 40 kilonewtons times 1, which is negative, plus 60 kilonewtons. And this will give you minus 30, but because you are doing the summation to the right, you have to change the sign and you will get the 30 as well. So from this cross section, maybe it's easier to calculate the moment to the right. When you have an UDL, remember that the variation of the moment under the UDL won't be linear anymore. The variation will be parabolic, so you need to connect these 2 points, 30 and 26, with this parabolic function. You can derive the reasons of that playing with the equations of moments, or simply calculating the moment at several points under the UDL, and you will see that what I'm saying is exactly like this, and you will produce a parabolic function. But the next point of interest to calculate the moment will be the point where you have applied 40 kilonewtons. And at this point, it's simpler to see the moment to the right, because if you are here, where you have 40 kilonewtons, and you do the summation of moments to the right, the only moment you have is 70 kilonewtons. That is positive, but you need to change this sign because you are doing the calculation to the right, so it's minus 70. And this is the reason why this 30 and this 70 is a sketch on top of the neutral axis, because they are negative moments. In between forces, the variation is linear. If you check the moment immediately before the moment here to the right, is still minus 70. And for this reason, the final value of the moment is minus 70 in this case, and you connect with the linear function that is in this case is constant because the two values are 70. Finally, the sign of the bending moment diagrams is positive when it's under the neutral axis, and it's negative when it's on top of the neutral axis. So the convention for moment is opposite to the shear force diagram. The bending moment diagrams give you an idea of the deformation of the beam, because the bending moment diagram, when it's positive, means that the fibers at the bottom of your beam are in tension and the fibers on top of your beam are under compression. And the opposite happens when you have the moment sketched on top of the neutral axis. In this case, the fibers that are in tension are on top of the beam, and the fibers that are under compression are at the bottom of the beam. So you can try to guess more or less the shape of the deformation of the beam using the bending moment diagram. The real values of this the form shape of the beam can be calculated with other equations, but we are not going to cover this in this module. But just it's interesting to see the connection between the deformed shape of the beam and the bending moment diagrams. If we put all this together, the thing we have done until here, so you see, you can see the relation between the diagrams and the structures you have resolved it until now. So in the first place, you have the free body diagram with the reactive moment, which is a positive moment, the positive reaction in the vertical direction, all the external forces applied to this beam and the distances. So the shear force diagram is the diagram that we have calculated. You see that where the shear force diagram is positive, that the shear force diagram is positive when it's sketched on top of the neutral axis, which is this one, and it's negative when you sketch under the neutral axis. But in the bending moment diagram happen exactly the opposite. So it's positive when it's under, and it's negative when it's on top. So this is just a detail to see the differences. We have said that there is a relationship between the distribution of moments and distribution of shear forces. So they are actually functions that are a derivative one from the other. So we say in general the shear force diagram is the derivative or the differentiation of the bending moment diagram. So we need to check the relationship in this way. So if we have a linear function from here to here in this interval, this must be constant because it's the derivative. So actually, the value of the shear force is the slope of this inclined line in here. Same thing in this interval and in this interval, and because these two should be actually parallel, because evidently the slope is the same value, as you see in the relation, but it's enough to recognize that a linear function derived will give you a constant shear force, a linear function for moment, a constant function for the shear force. In the interval where you have a parabolic distribution of moments, you will have a linear distribution of shear forces. Again, linear distribution of bending moments, constant distribution of shear forces. And in this interval, it's interesting because in this interval, you have a constant distribution of the bending moment, and the value of the shear force is equal to 0 because the derivative of a constant function of a constant is equal to 0, as you know from mathematics. So it's very important for you to check this relationship because they are very useful to interpret and to check diagrams and to find errors. So in an exam, for example, it's important if you find that in here you have a parabolic distribution and suddenly a constant shear force is something is not right, so you have to correct, because this is the actual or the correct relationship between these two diagrams you have on the screen. So this sounds easy when I explain it, but the ones that are trying to do by themselves notice already that when you try to do by yourself, you start having questions. So this is the idea. You try to resolve the exercises by yourself. When you find things that you don't understand, you can ask me questions during the class or via Teams or even by email, because the technique is super simple when you understand exactly the meaning of the shear forces and bending moment, but it's not that simple when you still not understanding exactly what we are talking about and how this is connected with the equilibrium as well. Because what we did basically, if we review, it will have decomposed the effect of all these external forces on the beam. So we have basically decided to work in the two-dimensional space. So we decompose the reactions in the horizontal and vertical direction and a moment. And after that, we have used these equations of equilibrium to work out the values of these reactions. And after that, we produced these diagrams. But these diagrams are telling you something very, very important. This means these diagrams, when you see the diagram is correct and is close, this means that the shear forces are in equilibrium at every cross section of the beam. And this tells you as well that the moments are in equilibrium at every cross section of your beam.